Okay, I guess you can see my screen. Thank you, Felix, for the kind introduction, and so for giving me the possibility to talk here about the research work that I've been conducting, actually collaborating with Felix and Matthias in NMR. To develop fully automated analysis of Photo-CIDNP NMR spectra for fast fragment screening. So here is a bit of background, but very, very brief background, since I think we all know what Photo-CIDNP and how with the radical pair mechanism between like a molecule and a photosensitizer is possible to enhance the sensitivity and the signal of NMR, and that this effect can be even stronger at low magnetic field, and it can be done at room temperature. What can be done also with Photo-CIDNP NMR is that we can really do fragment screening, so we can assess if a fragment is bound to a protein, and this happens because the signal enhancement of the Photo-CIDNP NMR is reduced when there is a binding and interaction between a fragment and a protein. And this kind of information that we can extract from the Photo-CIDNP spectra is an atom level information, because we have different reduction for different signals in the spectra, proportional to the binding strength of the atom, and also this can be done in like low concentrations of both the ligand and the protein. And since the enhancement of the Photo-CIDNP effect is quite large, is it possible to obtain like sufficient signal to noise ratio with just a single scan of NMR experiments? So this leads to actually a very fast production of data, but on the other hand, the manual annotation or the manual analysis of such data remains quite slow, burdensome. Sometimes it can lead also to some inconsistencies, some errors. And what are actually the steps of the analysis of a Photo-CIDNP NMR spectrum? So firstly, of course, there is it's needed a bit of preprocessing, because sometimes this kind of spectra can be a bit challenging, especially for what concerns the phasing of the spectra. And then after the preprocessing, one needs to identify which are the signals that are hyperpolarized, and this can be done by comparing the standard NMR spectrum, which I will also call in the following sometimes dark spectrum, and the Photo-CIDNP NMR spectrum, which I will also call light spectrum. And then, sorry, and then when the hyperpolarized signal are located and characterized, both in the free ligand spectra and in the ligand plus protein, then one needs to assess the intensity variation, which indicates effectively if the ligand has bound to the protein. And so since this can be quite a long pipeline of analysis, we decided to combine both traditional approaches and deep learning models to produce an automatic pipeline that is able to perform all these steps in like matter of minutes rather than maybe hours of work, and that can produce robust and reliable results that can really help scientists to annotate in the annotation process of the data. So the first step is, of course, the input. What does this pipeline takes as input? It takes, as I said, the dark spectra and the light spectra, so standard NMR spectra and Photo-CIDNP NMR spectra, both for the ligand only and the ligand in presence of a protein. And also it takes as input the molecular structure of the ligand. We are also tackling the possibility to consider several relaxation schemes. So to measure the spectra at different relaxation time and use them in the analysis as well. And then also to include several ligand concentration to also analyze titration experiments. Then we identify and characterized the hyperpolarized peaks. Here I'm showing an example of this, and this is the kind of the rules by which we identify such hyperpolarized peaks. So we compare the peak in the light and in the dark spectrum, and if the ratio of the intensity is over 2.5, we consider it as an hyperpolarized peak. Sometimes also, as in this case, the peaks do not really show in the standard NMR, and therefore we compare with respect to the noise level. After that, we also cluster the peak, the individual peaks into multiplets, and for that we are using a deep learning framework called MuseNet that I developed in the past years, and that is able to, as you may see, to detect the position of the multiplets, and actually also to classify the multiplets with respect to their splitting patterns. In this case, we are not using the multiplet splitting pattern information, and also it gives an uncertainty on the prediction, so that it's more reliable and trustworthy. And clustering the individual peaks detected into multiplets really boosted the precision of our algorithm, because the algorithm was able to detect all the hyperpolarized peaks already, but then it was over-peaking, but clustering the peaks into multiplets helped also to filter out unwanted peaks. And then at this point, we have on one side, we have the chemical shift measured from the spectra that we imputed, and we want to assign them to the atoms in the molecule that effectively produced the signals. And to do that, we also employed a graph neural network to predict from the structure of the ligand the chemical shift. And this is done by turning the molecular structure into a graph, where actually we are considering implicitly the hydrogens, and for which we have like an RMSA of 0.3 on the data set that we considered, 0.3 ppm. And then, so we have on one side the experimental chemical shift, and we have the predicted chemical shift, which they are also paired, of course, with the label of the hydrogen atom that produces the signal. And then we use a Bayesian inference to match, to perform a probabilistic matching between the experimental chemical shift and the predicted chemical shift, so that we can really pair the label of the hydrogens to the experimental shift. And in this case, so we are like, this is the traditional Bayesian equation, where the likelihood, so the probability of observing a certain experimental chemical shift y as a function of a given assignment A is given by the probability distribution, like Gaussian probability distribution, which is centered on each predicted chemical shift. And at the same time, we also needed to impose some prior on such probabilistic matching, a prior on the assignment. And in this case, we wanted the assignment, the resulting assignment, to be a partial matching in a way, because not all the signals that we observe in the experimental spectra are actually hyperpolarized. Actually, some signals are not even there, since they are not hyperpolarized. And also, not all the signals are potentially produced by the ligand. There could be some residual solvent or water peaks. So it's important to really be able to just match the peaks that we are interested in with the label for the hydrogens. And also with the Bayesian framework, we can impose some interesting constraints. So, for example, we know that usually the signals coming from here I said from heteronuclei, I meant from hydrogen bond to heteronuclei, are not usually observed, so that we can tune the probability to include this kind of constraint. And in the end, we end up with this matrix where it displays the probability of matching an hydrogen in the molecule with a given measured shift, and it helps the scientists to really get the most probable and most significant assignment. So once we have characterized the hyperpolarized signals, and we have assigned the hyperpolarized signal both in the free ligand spectra and in the ligand in the presence of a protein, we can compare finally the amplitudes of the signals, and we can assess if there was a reduction, and therefore if there was some interaction between the ligand and the protein. And one way to do this is to consider the binding contrast, where we just compute the ratio between the signal integral in the ligand plus protein spectrum and over the signal integral in the free ligand spectrum. And of course, this ratio is below 1. Therefore, the C-bind is defined between 0 and 1, with 0 being reflecting no interaction between the ligand and the protein, and 1 reflecting some sort of perfect or the strongest interaction between the two. But if we consider, for example, relaxation analysis or experiment, we can also compute this ligand score Q-bind, where we compute this ratio, where we firstly normalize the intensity both for the ligand plus protein and the ligand only over some reference spectrum, which is usually the spectrum with the lowest relaxation time. And again, this quantity is also defined between 0 and 1, and 0 for no interaction and 1 for perfect interaction. We finally we arrived to some results on screening dataset against the PGK1 protein. So we were able to define a EAT or a no EAT by thresholding the Q-bind, considering as a threshold 0.2. And these are the results. So we have above 90% correct detection of EAT and no EAT. At the same time, our pipeline is able also to, of course, tell if for some problem in the experiment there was no kidnap, no hyperpolarized signal to screen or to analyze, and therefore we were also able to detect those cases with a very high precision. The next steps to this work is, of course, to improve even further the quantification of the binding score, and related to this to the binding strength, the effective binding strength of the ligand and the protein, and then to analyze titration experiments to measure the dissociation constant for each atom in the molecule. and also to extend the algorithm to low field NMR, where the enhancement of the signal is higher, but then there are like other challenges related to like overlapping peaks and low signal to noise. I guess the take-home message from this talk was that comparing ligand only and ligand in the presence of a protein photo-kidnap spectra is a very powerful and effective approach to detect the interaction between ligand and protein, and that our algorithm was able to accurately and precisely identify and characterize the photo-kidnap signal automatically, which is really helpful for building a robust annotation strategies. And with that, I would like to thank my co-workers and supervisor at University of Venice, ZHAW, and also at NMR. And I want to thank you all for your attention.
Thank you very much, Giulia, for the very nice talk. It's really nice to see all those data again and to see them presented like this. We have some questions in the chat, and I will start maybe with the first one from Thomas Evangelidis, who is asking to which extent the graph neural network has been benchmarked for chemical shift, and was it benchmarked for more diverse structures than fragments, like drug-like compounds, and if you have the MSE and LMSD values for such compounds.
Yeah, so the network was benchmarked against the NMR DP. The NMR shift DP dataset was trained with that, and like, of course, splitting the data set between training and testing. And on that, we had, as I remember, an RMSA, or MI of 0.2, around 0.2 ppm. And on the NMR dataset, so the one that it was more targeted towards like ligand, it was performing even a bit better. So the MI was around 0.17 ppm.
Thank you. We have a second question from Alexei Kiryutin, who is asking on slide 12, what does T2 mean? I think he's confused if it was the delay or the relaxation time.
It was the relaxation. Yeah, it was this relaxation time. Yeah.
Okay.
Yeah. Well, yeah.
Yes, and I confirm, because this is our first program, so I confirm this is indeed for how long it relaxes, and not the delay in the first program. Then we have a last question from Marta Stefanska. Thank you very much for the great presentation. I was curious how the algorithm deal with the multiplet effect, so the plus-minus signal in the enhanced spectrum in terms of the assignment and intensity calculation. Are they ignored, or only one part of the positive is taken into account for the intensity, or do you simply process spectra in the magnitude mode?
So, well, at the moment, we are just considering the position of the peaks. So for assignment and also, yeah, for the assignment is not considered nor the sign of the intensity, and neither the multiplet splitting at the moment. We are considering also implementing or using the magnitude spectrum rather than like the positive and negative or the real spectrum as input. But so far we are not using it. It definitely maybe including also the multiplet splitting pattern or the sign could help the assignment.